Okay, for number 16, we have that A is a family of sets, which is indexed by the natural numbers, but it's a decreasing nested family, which means that for any two indexes belonging to the natural numbers, if I is less than j, then a sub j is a subset of a sub I. And so let me just put a diagram here to kind of help you guys see that. So say that this is a sub 1. So a sub 2, as 2 is greater than 1, it means that a sub 2 is going to be a subset. So maybe that's a sub 2. And then a sub 3 is going to be a subset of a sub 2 since it is 3 is bigger than 2. So maybe that's a sub 3, and then you would have a sub 4, and so on and so forth. So anytime you have a bigger index, the set that is indexed by the bigger one is contained within the set that is indexed by the smaller number. So now that we have that visualization, let's do item A. And now item A, we're trying to show that the intersection from 1 to k of a sub I is equal to the set a sub k. And so because we're trying to show equality, what we're going to do here is do a two-part proof. So first we're going to take some element that is here and show that it must be there. And then the second part, we're going to take some element that is here and show that it must be there. Because if we show a double inclusion, that is the same thing as showing equality. So we're going to say, maybe I'm going to put here part 1. Part 1. And for part 1, we are going to say let I, k belong to the set of natural numbers with I less than or equal to k. And now this is important because we're trying to show this nested idea, right? So we're going to say let x belong to a sub k. So we're taking some element here and trying to show that it must be there as well. Let x belongs to a sub k. And now we're going to say note that if I is less than k, then a sub k is contained within a sub I, right? This is this idea over here. And so thus, because we have said that I is less than k, so what that means is that thus, for all I less than or equal to k greater than or equal to 1, x belongs to a sub I. Because we said, hey, x belongs to a sub k. However, k is bigger than every single I, right, that is within this interval. So because k is bigger, it means that k is going to be included in all of these. So maybe you can picture that here that this is a sub k, and all the other ones are the bigger rings around it, right? And now notice that with this line here, we have produced the definition of x belonging to the intersection. So now we can just rewrite this as the definition. Therefore, for x belongs to the intersection from I is equal to 1 all the way out to k of a sub I. So we took some element that was here, show that that element must also have been there. So our conclusion is going to be, thus a sub k is a subset of the intersection from I is equal to 1, k, a, I. Okay, so that was part 1, right? We showed that ak is a subset of the intersection. And now we have to do part 2. We have to show that the intersection is a subset of ak. So for part 2, we're going to say let x belong to the intersection. So from I is equal to 1 all the way out to k, a sub I, right? So if x belongs to the intersection, what does it mean? Then for all, because this is the intersection, so for all I belonging, let me maybe just move this to the side so that it doesn't interfere with what you were doing. So I'm going to move this slightly over to the side, like so. All right. So we're going to say then for all I belonging to the set beginning from 1 to k, it must mean that x belongs to a sub I, right? If x belongs to the intersection, then for every index between belonging to the set from 1 to k, x is going to be in a sub I. Thus, x belongs to a sub k, because k, you can see here that k is within that interval, right? So thus x belongs to a sub k. So we began with x belonging here, and then we showed that x must be here. So our conclusion is going to be, therefore, the intersection from I is equal to 1 all the way out to k of a sub k is a subset of, oops, that should have been a sub I, is a subset of a sub k. So we have shown here a double inclusion, right? We have shown that, we have shown this, and we have shown that. So our conclusion is going to be, so conclusion, they are the same. So that is it for part A. We did a two-part proof showing a double inclusion. Now let's do item B. And item B is going to have the same structure in the sense that we're going to do a two-part proof and try to show double inclusion here. So let me erase all of this. All right. So for part B, we're also going, item B, we're also going to do a two-part proof. So for part 1 here, we're going to follow the same logic, and we're going to take some element from here and then show that it must be there. So we're going to say part 1, let x belong to a sub 1, right? If x belongs to a sub 1, we're going to have note that 1 belongs to the natural numbers, so there exists some I belonging to the natural numbers such that x belongs to a sub I, right? So we're saying, hey, if x belongs to a sub 1 and 1 is in the natural numbers, if our index is the natural numbers, therefore there exists some I belonging to it such that x belongs to a sub I, where in this case it means that I is equal to 1, right? This is not necessary for the proof, but just so that you guys can keep track of things. So since there exists, now this we have fit the definition, right? This whole line here, so there exists some I belonging to n such that x belongs to a sub I. This is the definition of x belonging to the union. So we can now just rewrite this definition. Therefore, x belongs to the union from I is equal to 1 all the way out to infinity of a sub I. So we took some element that was here, and we showed that that element must have been here as well. So it means that it is a subset. Thus, a sub 1 is going to be a subset of the union from I is equal to 1 all the way out to infinity of a sub I. Okay, so that is part 1. Now let's do part 2. So part 2, we're going to begin in the opposite direction. We're going to take some element that is here and show that that element must be here. So for part 2, we're going to say let x belong to the union from I is equal to 1 all the way out to infinity of a sub I, right? And we want to show if x belongs to the union, we want to show that x belongs to a sub 1. So let's expand the definition for x belonging to the union. So then there exists some I belonging to the natural numbers such that x belongs to a sub I, because that's the definition of x belonging to the union. And now we have note that 1 is less than or equal to I for all I belonging to the natural numbers, right? So I is greater than or equal to 1. And now remember what we said here, that the greater, if you have one index that's greater than or equal to the other, it means that that index is contained within the smaller one, right? So since I is greater than or equal to 1, thus it means that a sub I is a subset of a sub 1 for all I belonging to the natural numbers, right? Since I is greater than or equal to 1. So we're going to say as x belongs to a sub I, right? Because if x is in the union, it belongs to some a sub I. It therefore means x belongs to a sub 1, since every a sub I is contained within a sub 1. So similarly, we began with x belonging to here, and then we showed that x must be in a sub 1. So our conclusion is going to be, therefore, maybe let me zoom that out. Therefore, the union from I is equal to 1 to infinity of a sub I is a subset of a sub 1. So we have shown here a double inclusion, right? We have shown that, oops, and I wrote this wrong. This should have been a sub 1 here. So we have shown that a sub 1 is a subset of the union, and we have shown that the union is a subset of a sub 1. So our conclusion is going to be, these two are equal. So a sub 1 is going to be equal to the union from 1 all the way out to infinity. So that is it for item 16.